One, this is chapter 11.2, which is a discussion on series, opposed to what we saw previously, sequences. Series is just adding all of the terms in the sequence, basically. Now, it's an infinite sequence, so that means it'll be an infinite sum. So a series is the infinite sum. This notation is known as sigma notations, capital sigma, it's a Greek letter. So the way it's read is the sum from n equals 1 to infinity of a sub n is a1, a2, a3 all added together, and adding all of the terms in the sequence, actually, the sequence a sub n. So we say that a series converges if and only if the sequence s sub k of the partial sums of the series, meaning if you, instead of going to infinity, if you stop at a number, let's say k, you call that term the term of the sequence s sub k. So the sum n equals 1 to k of a sub n is a1 plus a2 plus a3 all the way to a sub k. We call that whole sum s sub k. And if you consider the sequence of s sub k, if that sequence converges, whatever that converges to, that'll be the sum of the series. So as an example, suppose we have a series of terms a sub n such that the partial sum, the kth partial sum, meaning stopping at some number k, is 2k over 3k plus 5 for all k. Meaning that if you were to actually find the first partial sum, it'll be 2 over 3 plus 5, so it'd be 2 over 8, which is 1/4. If you wanted to find the second partial sum, plug in 2 into this, and that'll give you the second partial sum. This honestly is a kind of weird scenario because the work is done for us. Usually with these kinds of problems where we want to find a series, we're given what each term in the sequence is, and to find the actual series, we have to figure out if there is a way we can find this kth partial sum. And if there is, we can generalize what the sums look like for every ending number k. Then we can take the limit of that general term. So now that we have that, well, this I think is okay because this here, this sum, is just the limit as k goes to infinity of s sub k. And since we know s sub k, the actual explicit form for s sub k is given to us, 2k over 3k plus 5, we can just find the limit of this however you like. If you want to divide everything by k, you'll get 2 over 3 plus 5 over k. 5 over k will go to 0, so it's just 2 over 3. It's one way of doing it. Another way of doing it is using L'Hopital's rule. Derivative of the top is 2, derivative of the bottom is 3, so it's 2 over 3. Another way of doing it is by what is called domination. So domination for limits at infinity are just looking at the highest powers and ignoring all lower powers of the variable, in this case k. So if you ignore all lower powers, like 5 is a lower power of k, it's k to the 0 technically, then you have, this is just the same as the limit as k approaches infinity of 2k over 3k. The k's cancel and you just get 2 over 3. Anyways, that was enough of this example. We'll take a look at a few other examples right now. But before we do that, I want to show you a specific type of series that is going to be very important in basically the entire discussion of chapter 11. So let's take a look at that right now. All right, so the specific type of series I want to take a look at now is called the geometric series. And the geometric series is the sum of terms a, where a is a constant, times r to the n minus 1. So if you plug in n equals 1 all the way to infinity, so 1, 2, 3, and so on, you get a times r to the 0, a times r to the 1, a times r to the 2, because of course the power will be 1 behind whatever subscript we're at, whatever indexing term we're at, basically. Now the first term is a, which is a non-zero constant, otherwise it's just a sum of zeros, and the common ratio is r. So that means that if you wanted to get from one term to the next term in the series, you would multiply by r. So that's one way to think of this. In fact, very often people consider what is called a geometric sequence in order to talk about a geometric series or geometric sum. But to get from one term to the next, we just multiply by r. So that's really what geometric means. There's a common ratio in place. Now here, the finite sum, or I guess the kth partial sum, adding up to k, if you plug in k, you'll get a times r to the k minus 1, so that's our last term now. And if you consider multiplying k by r, or s sub k I should say by r, each of these terms by distribution will be multiplied by r. So let me write that here. So we're going to get a times r plus a times r squared plus a times r to the third. So I'm just multiplying each of these terms by r and I get these. And if you multiply the last one by r, then you get a times r to the k. And the one before it would be, well, k minus 1. So just to show that, let me sneak that in between just like that. So the one before it would be a times r to the k minus 2, but multiplying that by r increases the power to k minus 1. And now what you notice is that a lot of these terms are actually the same. So now, if you subtract these actually, so if you consider now doing top minus bottom, basically, we have sk minus r times s of k is equal to, well, what you notice happens is a lot of these will cancel. Since we're doing top minus bottom, a survives the cancellation, ar doesn't, ar squared doesn't, ar cubed doesn't, all the way to, so all of these in between cancel, up to this one, and this last one is left over, but again, we're subtracting top minus bottom, so it's going to be a minus a r to the k like that. And notice here, if you actually factor out s sub k, what you have left over is s sub k times the quantity 1 minus r. Here we can pull out a, so we'll have a times the quantity 1 minus r to the k. And then look at that, if you actually solve for s sub k by dividing by 1 minus r, we get this general term for the kth partial sum, a times 1 minus r to the k all over 1 minus r, which is actually pretty brilliant that we can do that. So kind of like I said in the previous example, it's generally difficult to do this, but for this type of series, you can actually find the general term for the kth partial sum. And we can go beyond that in general. So now, as k goes to infinity, what happens? Well, as k goes to infinity, we have r to the k going to infinity. That's the only place k is actually located in, is in the exponent of r right there. So as k goes to infinity, we get the following. We get the sum now, because the limit as k goes to infinity of s sub k is just the series n equals 1 to infinity of a r to the n minus 1. And this is equal to the limit as this goes to infinity, as k goes to infinity of this, I should say. And by limit laws and a bunch of other things we saw in 11.1, r to the k goes to what? It goes to 0 as k approaches infinity only when r is in between negative 1 and 1. So this will actually approach a over 1 minus r only when r is in between negative 1 and 1. Another way of saying this is that the absolute value of r is less than 1. I'll write that in parentheses. There we go. Good. So we actually have existence of a limit of the series when, when r is in between negative 1 and 1. Otherwise, the series actually diverges, meaning it doesn't converge, of course. So that's good. Now we'll take a look at an example of a specific type of geometric series, and I'll even show you a little bit of a visualization as far as why it's called geometric, so that'll be a little fun. So let's take a look at that right now. Right, so for this first example here, we have the series as n goes from 1 to infinity of 1 over 2 to the n. Of course, this is the same as 1 over 2 to the n like this. And here, since the inside is less than 1, it's in between negative 1 and 1 specifically, we can actually say that this limit actually approaches the first term in the series, which is just plugging in 1. So the first term would be, so a in this case, would be 1/2. So it's going to be 1/2 over 1 minus the ratio. Now remember, the ratio is, well, what you multiply to get from one term to the next. And in fact, if you consider, this is a nice way of doing it, if you consider r being, let's say the next term in the sequence, so 1 over 2 to the n plus 1, over the term before that, so namely 1 over 2 to the n, we can actually write this as, well, 1 over 2 to the n plus 1 multiplied by the reciprocal of 1 over 2 to the n. And the n's cancel like this, so this is just 1 over 2. So it's 1 over 2 over 1 minus 1 over 2. So we really just get 1/2 over 1/2, which is just 1. Now there are other ways of seeing that. In fact, the best way of doing this is, hang on. Yeah, so the best way of doing this, I think, is writing it out. So if you actually wrote this out, plug it in numbers, you get 1/2 plus 1/4 plus the third term would be 1/2 to the third, which is 1/8, then 1/16, and so on. So from this, you can kind of just tell, well, multiplying from, getting from one to the other by multiplication to 1/2, this times 1/2 is that one, and so on. So you can kind of see it instead of just doing it in general, even though doing it in general is kind of the more mathematically correct way of doing it. This definitely works in practice. So it's just the first term divided by 1 minus the ratio. Now I said I would show you a picture. Now the picture I want to show you here is just a square. And there are other types of geometric visualizations of these types of series, but I think this one is really the one that hits home, at least for me. So really what we're going to do is we're going to consider this being a square of area 1. And if we cut this in half, like this, let's say, then the area of each side is 1/2. So if we shade one side, let's say we shade this side, what we have shaded is, well, a rectangle of area 1/2. So this will represent the first term in this series. If we look at what we haven't shaded yet, cut that in half, that'll be half that previous area. So now instead of 1/2, this area will be 1/4. So I'll shade one of those 1/4. That represents the second term in the series. And then 1/8 would be half of the remaining blank space. So if I cut that in half, like this, and then cut this piece in half, then this piece in half, all of these shadings, small shadings we get, are actually each term in the series. And what do you notice? This just fills up the whole square, basically. So all of these areas will add up to the entire area of the square, which is 1. So this is a nice way of showing that this series just amounts to 1 in the limit. There are, like I said, there are other nice geometric motivations or visualizations or geometric proofs, basically, of this idea here, but this just goes to show why it's called the geometric series, because geometry plays a role, actually. Now this one, to be quite honest, the second example is a little more difficult. It's definitely, there's a lot more going on. There's a lot of different ways we can actually approach this problem. The best way, I think, is just to take advantage of what I said earlier, plug in numbers and see what each of the terms look like. So let's try that just to get an idea. So when you plug in 1, you get 2 to the 2, which is 4, times 3 to the 0, so that's just 4, because 3 to the 0 is 1. That's the first term. Plus, plugging in 2, 2 to the 2 times 2, that's 2 to the 4th, that's 16, times 3 to the 1 minus 2, that's 3 to the negative 1. So really this is 16 over 3. Plus, the next term would be, well, it's going to be, we're going to plug in 3 now, so that's going to be 2 to the 6. 2 to the 6 is 64. And the denominator will be, since we're plugging in 3, this is 3 to the 1 minus 3, which is 3 to the negative 2, which means there's a 9 in our denominator. Okay, let's just do one more, just to see if we can figure out what's going on. By the way, if we want to write these as fractions, might as well write 4 as 4 over 1. Okay, just to kind of see the pattern here. And let's see if we can figure this out. So plugging in 4 now, because we're in the 4th term of the series, 2 to the 2 times 4 is 2 to the 8th. 2 to the 8th is, I think, 256. Over, well, let's see, plugging in 4, we'll have 3 to the 1 minus 4, which is 3 to the negative 3. That's 1 over 27. And so on. So, what you notice is that really this is 4 to the 1 over 3 to the 0, plus 4 to the 2 over 3 to the 1, plus 4 to the 3 over 3 to the 2nd, plus 4 to the 4 over 3 to the 3rd. Now, the subscripts we have, I guess the indices we're working with, are 1, 2, and 3. So to get a better handle on what the sequence is doing for each index, we want to compare to the index we're at. So namely, I want to write 0 in terms of 1, 1 in terms of 2, and 2 in terms of 3. So what's changing here, in the top is a power of 4, that's fine. But on the bottom is a power of 3, and it doesn't quite look like these numbers in red. But if I write this as 1 minus 1, 2 minus 1, 3 minus 1, and 4 minus 1, just like that, then we can actually tell that the general term here of the sequence of each term, that is just the following. It's 4 to the n over 3 to the n minus 1. And this is actually legitimately the same thing, because 2 to the 2n is the same as 2 to the 2 to the n, which is 4 to the n, and 3 to the 1 minus n is the same as 3 to the negative n minus 1, meaning it's 1 over 3 to the n minus 1. So if you're multiplying these two, it's really just dividing 4 to the n by 3 to the n minus 1. So legitimately it's this. Now if you take a look at the form we want, well, I don't actually have it written here, but the form we want is this. It's a times r to the n minus 1. We have an n minus 1 power for the bottom, but not for the top. We could actually write 4 to the n. Let me erase this and show you. Okay, there we go. We could actually write 4 to the n as 4 times 4 to the n minus 1, like that. Perfect. And then if we pull the 4 out of the fraction, this is the same as the series from 1 to infinity of 4 times 4/3 all to the n minus 1. Perfect. Now we're there. Now we actually have, well, we have the ratio. There's a problem though. What's the problem? Well, the problem, of course, is that the ratio is 4/3, and that's bad, because 4/3, as it turns out, is bigger than 1. Uh-oh. What that means is this series actually diverges. The sum doesn't exist. And that's all I'm going to say about this series. Of course, if the ratio was less than 1, then we can actually pull our trick and just say it's the first term, which by the way is 4, divided by 1 over the ratio, or 1 minus the ratio, 4/3. You can try that on your own, but if you try that, something funny is going to happen. You'll get a negative number, and these are all positive terms, so it doesn't make sense from that aspect. Some people tend to take that idea to the next level. I should have boxed this one, by the way. But some people take that idea to the next level and say that if you were to associate this sum with an actual number, even though it diverges, then you would do so by that number, just assuming that it works. But that gets a little beyond what we want to discuss. In fact, that's not our definition for a series diverging or converging. Our definition for a series converging is, well, it's when the sequence of partial sums converges, and in this case they don't, because, well, the sequence gets larger and larger, so the limit doesn't exist. So since the limit of the sequence of partial sums doesn't exist, then the series doesn't exist as well. Anyways, it's still a kind of fun example to see. So now we're going to take a look at something a little different. There's not really too much more to discuss in this section, but we'll take a look at what we can before moving on to the next big idea in 11.3. Right, so here we have a theorem and then the consequence of the theorem. It's actually the contrapositive of this theorem. But anyways, the theorem says that if we have a series that converges, then necessarily it must be the case that the sequence of each term in the series must go to 0. So the limit of the sequence must be 0. Now, that should kind of intuitively make sense, because if that's not the case, if it's the case where the terms don't approach 0, don't get smaller and smaller as you write terms in the series, if they approach some other number, let's say they all approach 1, then if they get closer and closer to 1 in the sequence, then that means in the series, you'll eventually have numbers that are close to 1, so you'll have infinitely many 1s basically in your series, meaning that it would approach infinity and be divergent. That's just one idea though, but in fact there's a really nice way of proving this theorem, and it's kind of interesting. So the biggest, I guess the the way to prove it would be the following. So if you were to consider the partial sum S of k, and so S of k would be a1 plus a2 all the way up to a sub k. And then if you consider the next partial sum, S of k, let's say plus 1, well, this is a1, a2, all the way to a sub k, and then one more term, a sub k minus 1, plus 1. Meaning, if you were to combine these by subtracting, S sub k plus 1 minus S sub k is just equal to a sub k plus 1. You could also do this with a different subscript, but this way works as well. Now notice, since we're assuming that the series converges, then that means that the sequence of the S sub k's converges, so we can say the limit as k approaches infinity of S sub k exists. We can call it S, let's say. And notice from an argument we saw earlier, this is the same as saying the limit as k goes to infinity of S sub k plus 1. I believe we actually saw this argument in 11.1, but this is certainly true. And in fact, if we were to, let's see, if we were to subtract these, they're both equal to S. So in fact, we can say the limit as k goes to infinity of a sub k plus 1. Well, a sub k plus 1 is just equal to what? A sub k plus 1 is just equal to S sub k plus 1 minus S sub k. We know from this, since they're both equal to S in the limit, this is just, well, the whole thing really. Since limit of the difference is the difference of the limits, this is really just, well, S minus S, which is 0. So that implies that the sequence goes to 0. Terms in the sequence go to 0. So that really finishes the proof there. So it's a quick little proof. It's not too bad. It's kind of nice to see. But now what that brings up is this. This is probably one of the most useful, I guess, applications of the theorem, and that's the test for divergence. And basically it says that you can actually tell if a series diverges rather quickly if the sequence that are the terms of the series, if they approach a number that's not 0, or if the limit does not exist, then we can say right away when the series is divergent. So a quick example, let's just say we want to consider the series n goes from 1 to infinity of, I don't know, how about n squared over n squared minus 1. So you could write out a few of these terms and just see what it is. So it's going to be, maybe I should make this plus 1, otherwise we get 1 over 0 for our first term. Let me think about that for a second. That's fine, I guess. But minus 1, even though the first term is bad, after that, it'll still have the same idea. So when you plug in 1, you get 1 over 2, plus the next term plugging in 2 gives you 4 over 5. And then the next one, 3 squared is 9, so it's 9 over 10, and so on. Now, by the test for divergence, so let me call that TFD for short, since the sequence n squared over n squared plus 1 approaches, well, that actually approaches 1. A few ways to see that. If you consider domination, ignoring the plus 1 on the bottom, as n goes to infinity, the n squared dominates over 1. N squared over n squared is just 1, so the limit is 1. So as you go further and further out in the sequence, or I guess in the series, each term will get closer and closer to 1. So kind of how I previously mentioned, eventually the terms will be all 1s, basically. So you'll have infinitely many terms in this series. So that means you have infinitely many numbers that are really, really close to 1. So your answer is going to be an infinity in the limit, actually. So since this sequence, the sequence of the terms of the series approaches 1, this implies that the series diverges. All right. Now I want to take a look at some other examples that are kind of, maybe not a counter examples to this, but there are examples that will make you think twice about applying these ideas. So let's take a look at those right now. Right, so at first these two examples seem kind of similar, but they're actually very, very different. So the first one, if you write out a few of the numbers, you certainly can do that. I don't actually want to do that. Instead, what I want to do, I'm just going to cut to the chase. So what we can do actually is we can split this up using an idea from partial fraction decomposition. So the inside part, that is, the general term of the sequence that we're taking the sum of, we can actually write it as, if you factor the denominator, notice n squared plus n factors as n times n plus 1. So we can write this as something over n plus something over n plus 1. And it doesn't actually take too long to figure out what these letters A and B are. In fact, if you combine them back into one, you get A times n plus 1 plus B times n all over n squared plus n. We want the numerator to be 1. So the only way that'll be the case, actually, you can kind of see after distributing this, it must be the case that, well, if you just look at this, so you get an plus n plus bn, and for that to be 1, well, these must cancel, so that means b is equal to negative a, actually. And at the same time, a must be 1. So a and b must be 1, but b is negative 1. So we must actually have this. So it's not too bad to see that. In fact, this is definitely the case. So now what we're going to do, so this is still, we're taking the sum of this one thing, and we can actually plug in numbers now. But what I want to do is I'm going to consider the partial sum up to k, and then from there we'll take the limit as k goes to infinity, which we can do. And what you kind of notice is that since we've written this as a difference of a sequence involving n and a sequence involving n plus 1, they'll have a lot of things in common, and since we're subtracting here, we'll actually get cancellation. So if we let s of k equal the sum from n equals 1 to k of this guy, 1 over n minus 1 over n plus 1, well, let's see. So if we actually write it out, the first term, let me use parentheses, I guess, we get 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3. So that's basically how this is going to look. We start by plugging in 1, and we get 1 over 1 minus the next one, 1 over 2. And then when you plug in 2, you get 1 over 2 minus the next integer, well, the reciprocal of the next integer, 1 over 3. And the next one is, well, it's going to be 1 over 3 minus 1 over 4. And it's going to go on and on like this until we get to the last one. In fact, if you want, you can show the second to last one. So let me try to make more space to show that. So the second to last one is going to be 1 over k minus 1 minus 1 over k. And then finally the last one, hopefully I have a space here, is going to be 1 over k minus 1 over k plus 1. Kind of ran out of space there a little bit. So notice what I said earlier, there's some heavy cancellation going on here. The 1/2 cancel, positive or negative. The 1/3 cancel, the 1/4 cancel, all the way. So there's a bunch of cancellation in between. These cancel, and then finally the 1 over k's cancel. So the kth partial sum of this series is actually sk equals everything that didn't cancel, which is just 1 minus 1 over k plus 1. Fantastic. And if you take the limit as this goes to as k goes to infinity of s of k, well, what you'll notice is you'll get 1 minus 1 over infinity, which goes to 0. So it's just 1 minus 0, which is 1. So in fact, that actually is the sum of the series. So it converges, and moreover, it converges to 1. Nice. Also notice from what we saw from the previous theorem, the sequence here, 1 over n squared plus n, will actually go to 0. So this doesn't diverge. Now, that idea is only one way. It's not two-way. It's not biconditional. Meaning, if the series converges, which it does, then it must be the case that the sequence of the terms goes to 0. This is a counterexample to the contrapositive, or I guess not contrapositive, but it's a counterexample to the converse. Here, 1 over n goes to 0 in the limit, the sequence goes to 0. But the series doesn't converge. Strange. So this is actually 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on. And this is something we'll kind of analyze a lot in chapter 11, and different kind of versions of this. This is known as the harmonic series. In fact, I've shown in class already, well, kind of shown in class. I gave you an extra credit problem anyways, where I asked you to show using Riemann sums that this actually diverges. So in fact, there are a lot of different proofs that the harmonic series diverges, and we'll see more of them actually as the class goes on. But I'm going to show you a kind of elementary way, and I may have shown this in class actually. But basically what we'll do is we'll go up to, I guess we can go up to 1/8. No, we can probably go up to 1/16. It's going to be a lot. So maybe, I'll pause the video and I'll write out all those terms out right now. All right, so far what I've written here is the first 16 terms in the series, and then of course it goes on, so I wrote ... And what we're going to say is we're going to say that each of these is greater than, so term by term, each of these are greater than the power of 2 that they lead up to. So for 1 and 1/2, they're each greater than 1/2. Well, 1/2 is bigger than 1/2, but 1/2 plus 1/2 is bigger than 1/2 plus 1/2. So we can say this without equality, but if you want to write or equal to, I guess you can, it's fine. And here we're going to say this is bigger than 1/4. And for these, we'll actually go up to 8. So this is 1/8. I missed a 7. So let me squeeze that in there. There we go. So we'll have 4 1/4. So actually, we're going to 8. I'm sorry, we're going to 8. So we have 4 1/8. There we go. Sorry about that little hiccup there. Perfect. And then the next power of 2 is 16. And how many are there? Well, you can count. We'll have 1, 2, 3, 4, 5, 6, 7, 8. So the amount of terms you have basically doubles. In fact, maybe we should have left this 1 just to show that. But there would be 1 1/2, 2 1/4, 4 1/8, and then 8 16s. So in fact, I'll write that as 8 times 16. And then plus ... So you can do the same idea throughout. So if you want to go up to 1/32, you'd have 16 terms that are each greater than 1/32. Okay, so now, the reason why we're doing this is because, notice this is 4/8, which is just 1/2. Also notice 8/16 is just 1/2. And actually this ... right here, if we continue this type of pattern, we basically get infinitely many 1/2s. So notice it's no coincidence. This is also 1/2. And here we already have 2 1/2s. And the reason why this is, I guess, not good is because 1/2s pair up to give you what? 1s. And what did I say is bad about having 1s in the series? If you have infinitely many 1s, then they add to infinity. So this will approach infinity. So we have shown that this sum is greater than or equal to something that approaches infinity, so it must be infinite. So this shows that this actually diverges. Now, like I said, there are other ways of showing this. I think probably better, shorter ways of showing this. But this is the most elementary proof of the harmonic series being divergent. The last thing I want to show you in this section are some properties of series. Basically, there's addition, constant multiple, and difference properties. It's nice to see them, so let's just take a look at those to finish off the section. Right, so here we say that if the series of a sub n and b sub n are both convergent series, then the following 3 things are true. Well, there were 2 things, but the second one's really 2 and 1 are true. So the first one says you can pull a constant multiple out of the series. The second thing says that a sum or difference can be passed through the series. So the sum of a difference or the sum of a sum is the sum of the series or the difference of the series, basically. Now, I'm not going to prove these, but I will say that the reason basically why these are true is because it's true for the partial sums. It's true for a finite sum, which makes sense because really the first thing is just saying we can factor out anything they have in common. Any constant multiple that they all have in common can be factored out of each of the terms. So you can factor that out of the sum, and in the limit, if the series of a sub n converges, then this would have to converge as well. And the same thing we can say here, if you kind of consider rearranging terms, the series of a sub n and the series of b sub n if you consider their partial sums, finite amount of terms, you can rearrange them so that a sub n's and b sub n's are together, and then you get that, well, this series would have to be equal to the sum or difference of two convergent series. So that's kind of the main idea there. Now, for this example, we'll actually be using the plus version of the second one. Now, it turns out each of these, and we've actually seen both of them in this video, they actually converge. Well, we've kind of seen the first one, but let me try to explain. So what I'm going to do is I'm going to write this as, let me write it like this, 3 times 1 over n squared plus n, as n goes from 1 to infinity, plus the series as n goes from 1 to infinity of 1 over 2n. Now, 3 is a constant, so we can pull it out because the series of 1 over n squared plus n actually converges, and only because of that. Now this we actually saw in one of the previous examples. 1 over n squared plus n actually approached 1. And we actually saw this in a previous example of this video as well, though not as recent. This is just, well, this is a geometric series with common ratio 1/2, and the first term is 1/2. So it was 1/2 over 1 minus 1/2, which is 1/2 over 1/2, which is also 1. So in fact, this whole thing just equals 3 times 1 plus 1, which totals to 4. So that means the original series has, well, sum 4. Awesome. So that concludes 11.2. Really hope you enjoyed it. We have a lot to look forward to in chapter 11. So I'll see you in the next few videos. It's going to be a lot of fun. Thanks for watching. See you then.